welcome everyone. I'm not going to be able to see your reactions, so I'm just going to pretend that everyone's enjoying themselves as I go along. And if I ask questions, I'm just going to sort of also make up the answer in my mind of what everyone's answering. Yeah, the name of my talk is Anime-ify Yourself using Coreml, and I'm Yono. So who am I? So most of you know me, it looks like, so this introduction slide might be a little bit redundant, but along with Alice Zhao, I'm the co-creator of Gus on the Go, which is this owl guy right here. Gus helps introduce young children to new languages at an early age and tries to make them better global citizens, which I think we need more of nowadays. I'm a freelance software developer. I've done everything from back-end development to web development to mobile, and currently I specialize in computer vision and machine learning in iOS. I also am a tutorial writer for the iOS team on raywinterluck.com, and most of my tutorials end up having to do with the vision framework or the camera. And right now I am watching all of Futurama while exercising on a stationary bike. I mean, like, not right now, I'm not exercising on a stationary bike right now, but during my morning routine, I am rewatching all of Futurama. So that's a fun fact, I guess. All right, let's talk about converting a model to Coreml, because that's what you all came here to see, I guess. But first, let's talk about what is a model. And you can think of a machine learning model or a deep learning model as nothing more than a function. And this function can have one or more inputs. It can have one or more outputs. And it has various parameters. And these parameters are usually broken down into two classes: weights, which are multiplied, and biases, which are added. And if the biases are negative, then they're essentially subtracted. Now, this function here that I have here is not a very interesting model, but it's just a simplified version. You might have something like image classification, which image classification model takes input as an image, and it spits out the class of the image. So it's determined that this is a face. You wouldn't normally have a classification for a specific person, like you wouldn't have something that spits out Yono, but you would have face or human or person or man or something like that. Another type of model that's similar but different is object detection. And object detection models take in an image, but instead of spitting out a classification for the entire image or what the main focus of the image is, it tries to detect individual items inside the image. So in this case, we might be looking at different parts of the face. So it gives you the bounding boxes of various parts of the face plus their classification, which might be eye, nose, or mouth. And in this case, it's similar to image classification, but more detailed. Completely unrelated to vision, but somehow related, might be text generation. So a text generation model will take in a prompt and it'll spit out the rest of the sentence or a paragraph or an article. And often it's just nonsense anyway. So you might have heard something like GPT-3 or BERT or something like that. Those are the classic models nowadays that do text generation. But at the beginning, I mentioned that a model is a function, and functions need numbers to work, right? But all these examples I showed you were images or text. So we need a way to bridge these two concepts of models being functions, but models taking something other than numbers. And we can do that by encoding the inputs into numbers and then decoding the numbers that the model spit out into something that you and I can understand, like an image or other text. So images are fairly easy when you think about them. They're nothing more than very large arrays of pixel values, and those pixel values are numbers usually between 0 and 255. And you have dimensions for the height, the width, and then the channel, which could be red, green, or blue, usually. The values that you use for the pixels as input or output are going to be dependent on the model, and it's important to pay attention to this. So this is kind of like a foreshadowing for later. This is what people in the business called foreshadowing. So it might be, a pixel value might be anywhere from 0 to 255, which is what we normally think of it as. But you could also have a range from 0 to 1.0, or from -1 to 1, which is a little bit more unusual in, say, iOS land, but it's very common in machine learning. Text can also be encoded as integers. A language is nothing more than a finite number of words. There might be tens, hundreds of thousands of words, but it's a finite number. So you can assign each word, essentially, a value. And this value can then be encoded as a one-hot vector, which can be passed into a model. So you might have the value for this or this, doesn't matter if it's capitalized or lowercase, might be 55, and talk might be 743 as an example. So with that in mind, our models are still functions, and they can now handle images as inputs and outputs, and text as inputs and outputs. Frameworks that are used to create models, the most popular ones nowadays are going to be PyTorch and TensorFlow. And because we're an iOS or Mac development crowd, let's go ahead and throw in Turi Create and CreateML in there. CreateML is nothing more than like a graphical interface to Turi Create, I believe. So it's all the same thing under the hood. But that's what you would use if you wanted to create a model directly into a format that Coreml can handle without having to go through a conversion process. There are other frameworks, but they're kind of esoteric or not as widely used or up and coming, but these ones are the main ones. And I have to also mention Scikit-Learn, because if there are any machine learning fundamentalists here, they would be pissed off if I don't mention this, and I just want to cover my bases so I don't get like angry emails or anything like that. But Scikit-Learn was around for a long, long time. It's a machine learning framework. It's probably one of the oldest ones, and it doesn't do anything with, I don't believe it does anything with deep learning or anything like that, but it has like the classic machine learning algorithms like SVM and decision trees and stuff like that. And if you don't know what that means, it's okay. It's probably not that interesting. Okay, so the Pi in PyTorch, that stands for Swift, right? Well, unfortunately not. It stands for Python. So we're going to be talking about Python a little bit in this talk. And I'm going to ask how many people have used Python before, and I'm going to just guess maybe 15%, 20%. I won't know. So you can tell me after the talk. But this is one of my favorite XKCDs on Python, just because this is, when I learned Python back in 2006, this is kind of like how it felt. It felt like you could just import something and suddenly your program was done. It was offering so much functionality with these frameworks that you can easily import. I know nowadays people say dependencies are bad, but these are some powerful frameworks that you can import and then work or improve upon and build upon. So it makes things fairly simple. You do have a little thing with white space, like he mentions. There are no curly braces or anything like that. So the way you know if you're in a function or in a class depends on how many spaces you're indented in, and they have to be consistent. If you're not consistent, the Python interpreter will throw up an error. It's maybe a little bit jarring at first, but you get used to it, it's fine. And then it makes it kind of readable. So, and XAC always has alt text. So here you go, in case you want to see. This is also very apt because the first time I started learning Python, I felt like I was able to write things fairly quickly. And I often found that because I could write an interpreter and in a script at the same time, it was easy to get things to work fairly, almost sometimes the first try, sometimes just with a couple of tweaks. So, but I've gotten off the subject of models, so we have to go back to models for a second to find out some things. So not these kinds of models, but these kinds of models. So where can you find models? Models are thankfully nowadays fairly easy to find online and almost anywhere. Most of the frameworks I mentioned before have built-in models that you can just import and then use immediately. So for instance, PyTorch has a Torch Vision framework, which has a bunch of computer vision related models that you can just use right off the bat. TensorFlow has something similar. They bury it under a longer set of submodules, but that's just because of the historical way that it was put about. And these built-in models are really easy to use. Here's the example of how you import from Torch Vision and import from TensorFlow. And essentially, you can just download the model and you can have a pre-trained model immediately. The pre-trained here true or the weights ImageNet, that's generally what you're going to do is a lot of these kinds of models are going to be pre-trained on a data set called ImageNet. ImageNet was, might still be, I'm not sure, a competition in early machine learning that was trying to classify images into 1,000 different classes. And when deep learning came on the scene, deep learning kind of took over and completely beat everything that was out there before. I don't want to throw out numbers, but I'm going to because why not? I think before deep learning came on the scene, like the accuracy on most ImageNet competitions, like the maximum was like 30–40% or something like that. And then when AlexNet came out, one of the first deep learning models, they did something like 72–75% accuracy on ImageNet. And the following year, or the next 2 years, almost all of the other teams had converted over to deep learning in order to compete in ImageNet. And it's a hard problem when you think about it because you have to take an image and classify it into one of 1,000 different categories. So these weights are usually pre-trained on ImageNet, and the reason is because it's thought to be fairly generic images, and a lot of times you can learn basic forms of basic vision forms and shapes on these generic images, and then fine tune them to your special need later on. Okay. There are also model hubs, and PyTorch has a PyTorch hub, which I believe anyone can supply models to. They have the search online where you can actually find a bunch of different models that you can use. And there's some overlap with their built-in ones, but there's also some things that are not included there. TensorFlow also has TensorFlow Hub, which is a similar type of thing. And the nice thing about these hubs is just like the built-ins, it's basically a one-liner to download the model and you're up and running. So it's fairly simple. Torch uses this torch hub.load function, and TensorFlow uses a TensorFlow hub.load function. And again, you have the option for pre-trained or not. And then there are something called model zoos. These are, what's the difference between a zoo and a hub? My personal feeling is that zoos tend to not be integrated into the framework itself, and hubs are hosted by the frameworks. So for a zoo, you would download the model separately and then manually import it into your code. So this one is one I just Googled and found modelzoo.co, which had a bunch of different things that you can find and get started, which is pretty cool. And of course, Apple also has their own model zoo, which has a bunch of already trained models in the Coreml format. So if you're going to use these ones, you don't actually have to follow the rest of this presentation on how to convert to Coreml because you already have it in Coreml. So that's kind of cheating. Yeah, so models are everywhere, right? Everyone can get a model from anywhere they want. They're freely available online almost all the time. People like to take these models and build upon them, so it's awful. But where else can you find models? Can you find models on, say, Twitter? And the answer is surprisingly kind of. So this is how I initially found out about Anime-IFy version 2. I follow an account that tweets a lot about machine learning and deep learning stuff, and suddenly I noticed he was retweeting, or she was retweeting, I don't know who it is. They were retweeting a lot of other people's images of showing side-by-sides of the original image and this like Anime-ified image. And I thought, this is kind of cool. And it was happening for several weeks that I noticed this. And luckily, if we go back to the original tweet, I noticed there was a GitHub link. This tweeter had the foresight to also, in addition to having a demo where people could try it out, he had a GitHub link that I think we wanted to visit. So we take a look at the GitHub, and it looks pretty good. There's a PyTorch model. Very nice. Even better, you see this hubconf.py. if you were to search PyTorch's online hub directory, you would not find this model. However, because he included this hubconf.py, you can use PyTorch's hub load functions to download and install this model directly in one line, just like as if it were part of PyTorch Hub, which is really cool. And here are some examples from his repository on famous people converted into anime. And this looked really cool. Something you might notice when you look at each one in a little bit more detail, one thing that the model seems to do is, besides simplify and give it a drawn style, and it also simplifies the hair, which is actually really cool because that's not something that's been done very well in the past. But what's also you might notice is that people's eyes get a little bit bigger, which gives it a little more of that anime feeling to it. The lips get also a little bit puffier, so it becomes overall kind of a cartoonish look. And I especially like Bill Gates's down in the bottom right-hand corner, where the shadow from his glasses on his eye start to look like a tattooed teardrop next to his eye. So, you know, he's what does that mean? He's killed someone, or he's had someone who's been killed, something like that. He's definitely a gangster, though. All right, but we don't want a PyTorch model, do we? PyTorch doesn't help us in our iOS apps. We want a Coreml model. So we have to wade into Coreml Tools. And Coreml Tools is an open source project from Apple, which helps you to convert from the more popular frameworks into Coreml using Python. So you're going to have to get your hands dirty with Python into this. If you're not familiar, we're going to also go through all the steps of getting an environment set up. So don't worry. So these popular frameworks include PyTorch, which we've talked about several times, TensorFlow, also talked about several times, and Scikit-Learn, which, of course, just to appease the machine learning purists. Yeah, you can also use Coreml Tools to optimize Coreml model. So you can read it, write it, and optimize it. Or not necessarily in that order. You probably want to read it, optimize it, then write it. And on Macs, not on Linux, but on Macs, you can use Coreml Tools to actually also run inference, which means you can run the models through Python, which is great for debugging and great for comparing to output of the model that you converted from. All right, so Coreml Tools a long time ago. This is a story from yonder years from my experience. And this happened in 2019. Who knows when 2019 was? It was such a long time ago at this point that no one remembers it anymore. But I remember one story from 2019, and that was I was working on a project, and I wanted to. Google had just released the model EfficientNet on TensorFlow. This was their own research. They had released this model, and I wanted to use it for a project that I was working on at the time. However, I was working on an iOS app, so I needed in Coreml. So I went to Coreml Tools, and Coreml Tools back in 2019 was able to convert from TensorFlow to PyTorch. TensorFlow to. Turns out what happened was TensorFlow had used, or sorry, not TensorFlow. Google had used a new kind of layer in this architecture that had not yet been ported over to Coreml. So Coreml has to know about everything that it's converting, and unfortunately, this was a new architecture that it had never seen before. So it just failed. So I started hunting around a little bit, and I was like, well, what can I do with this TensorFlow model? Well, I was able to convert it to PyTorch. Back then, you couldn't convert PyTorch to Coreml without first going through ONNX, ONNX, which is kind of like an open platform description of neural networks. They were trying to be like an open standard for how neural networks could be defined. So in 2019, in order to convert from PyTorch to Coreml, you had to first convert to ONNX. I couldn't convert from ONNX to Coreml, though, because this layer that TensorFlow had was also in PyTorch, and PyTorch just converted it over to ONNX. And so there was still this layer that Coreml did not know what to do with. So that failed. However, after a little bit more digging, I converted the ONNX model into Caffe2. Caffe2 no longer exists. I believe it was somehow engulfed, eaten, merged into PyTorch or something like that. But anyway, back then, Cafe 2 had a converter to Coreml, and Cafe 2 had a converter from Onyx. And interestingly enough, this weird layer, when it was converted from Onyx to Cafe 2 also didn't know about this weird layer, or at least it didn't have a special layer for this weird layer, but it knew how to convert something similar to it. So what it did was it took the specification from Onyx, converted it into a layer that it knew how to use that was essentially equivalent, or a couple of layers that were essentially equivalent. And then from Cafe 2, I was able to convert to Coreml. That was super easy, right? I mean, straightforward. Well, today, well, not today, but like a couple of days ago, I wanted to see if I could just convert the same model from TensorFlow to Coreml, you know, in the future or in the present, and it worked just fine. So this model is also available in PyTorch, and I noticed I could convert that very easily straight into ML. I didn't have to go into Onyx. So what happened? Back in 2019, the Coreml team essentially had to, or the Coreml Tools team had to know about a whole bunch of different frameworks, and they had to write separate converters and optimizers for each framework that were compatible with Coreml. And this was a slow and laborious process. Additionally, we all know that Apple doesn't have the most quick release schedule. They tend to have a yearly release schedule. So anytime there was an update, Coreml Tools also wasn't necessarily going to get it right away. So things tend to lag behind a little bit. Today, besides the fact that there aren't as many other frameworks to deal with, what they do is they first convert TensorFlow and PyTorch into something called MIL, which is a model intermediate language. And this model intermediate language then gets optimized for Coreml. And this model intermediate language is kind of like a bunch of different operations. And they have a bunch of basic operations that they can use. So interestingly enough, if they come across something that can't be converted, almost often what you can do is just use a bunch of these built-in operations that it already has to simulate the very same thing. Interestingly enough, there is actually a newish layer that's used in Anime-GAN version 2 called group norm. And when I first saw this, I started to have flashbacks to 2019. I was like, oh, this is not going to work. After some more digging, I found they had already implemented Coreml Tools using MIL ops. So they had already gotten around the problem using this new methodology, which was great. And when I looked at the conversion, the operations used to implement this group norm were not super sophisticated. So had they not already done that, I felt somewhat confident that I could have done it myself too, but I guess we'll never know now. All right, let's go back to this Python environment. Let's set up a Python environment to find out how we can run all this stuff. And that brings us to our second XKCD for today. And anyone who has used Python before is going to nod their heads profusely at this. And yeah, essentially there's 1,001 ways to install Python and all the frameworks that are associated with them. Mac OS comes with Python 2.7, which is terrible. Python 2 and Python 3 are not compatible. Almost everything has moved on to Python 3. There's very few stragglers left on Python 2. 10 years ago, that was not the case. 10 years ago, a lot of things had not moved over yet. There's a million different ways to set up an environment in Python. It feels like anyway. And if you haven't been paying attention and you haven't been doing it consistently, you might have Python, bits of Python binary and frameworks and libraries all over the place. And it's maddening. But what we're going to do is at the top here, I don't know if you can see my cursor, but this Anaconda Python, we're going to focus on that today because Anaconda allows you to build environments and keep them kind of self-contained. And as long as you follow a few simple rules, you're not going to create this mess of a Python environment. And of course, the alt text, in case anyone wants to see that. I'll let you read it. I'll give you 10 seconds. All right. So Conda, or it said Anaconda before, people short it Conda. This is the environment that we're going to use. Conda allows you to create separate environments for whatever you want. You can do it per project. You can do it per anything actually. So for instance, if you want to support Coreml Tools on one project, but you need to have an older version, for instance, like say you need Coreml Tools 3. You can have a separate conda environment for Coreml Tools 3, or you can have a separate conda environment just for that project, named after that project, that has the specific packages that you need for that project. This makes it very nice to switch between projects without having to wonder why your environment is messed up. So this keeps everything in sync for you, which is nice. So how do you set up Conda? There are a couple of ways to install Conda. However, the easiest is through Homebrew. So if you haven't installed Homebrew, you probably should, because it makes it much easier. But that's going to be left as next for the user. And you start by installing Miniforge, brew Miniforge, brew install Miniforge. And Miniforge is a minimal installation of Conda. As you can see, it'll download a bunch of stuff, start extracting, installing, linking. I don't know how long it normally takes because I don't know that this was on a fresh machine. After you install Miniforge, you want to do a conda init and then your shell. It could be ZSH or it could be fish, it could be bash, whatever you want. But you need to do this in order to have conda install a bunch of path related stuff into your shell. The next step is restarting your shell or terminal app because, you know, it needs to rerun. When you bring it back up, you'll notice that it says base here in the upper left-hand, or next to your path. And this is the base conda environment. Whatever conda environment is currently active will be by default in that, will be labeled somehow. On my fish shell, for instance, though, it's on the right-hand side. On ZSH, it's on the left-hand side here. But we're going to start by creating our first conda environment, and we're going to call it Coreml because that's what we're going to be using it for. And the path, the command to create it is just conda create -- name, the name that you want to call it, and then you want to specify a Python version. In this case, we're specifying Python 3.9, which is the newest version of Python that conda supports. It'll actually install the highest dot version that it has. You want to say yes, and it'll start installing everything that it needs for Python 3.9.7 and supporting libraries. This may take a while, depending on the speed of your machine and your internet connection, but once it's done, we'll then conda activate our environment. And what this does is you'll see that base in the bottom left-hand corner, you'll see that change to Coreml once we've activated the environment. We then want to install our packages. And in this case, we're going to install PyTorch and Torch Vision. We do that through a conda install. And anytime you can install something, anytime you want to install a package for your conda environment, you want to first try using conda install. Sometimes it's not going to work, as we see in a little bit, but first let's let it finish installing PyTorch and Torch Vision, which we're going to use for helping us convert to Coreml. Because how can we convert to Coreml if we can't read the Python or the PyTorch model to begin with? You'll notice that it's installing Torch Vision 0.10.1 and PyTorch 1.10.0. Those don't have to match. That's okay. They're just different versions for those two different packages. Okay. After we've installed PyTorch and Torch Vision, we want to install Coreml. Coreml Tools. But Coreml Tools is unfortunately not available under conda install, so we have to use pip install. We can fall back to pip install because the Python environment that we installed automatically installs pip. Pip is a package manager for Python that's in or comes with it, and it can install a lot of things too. In this case, we're installing Coreml Tools 5.1. This might be a lot of stuff to throw at you at once, but I will have a document of this, like how to do it, on the GitHub repo later so that you can follow along more easily. And if you want, you can also install Jupyter Lab, which is super cool, but completely optional. Jupyter Lab will allow you to run Python interactively in a browser, and you can set up cells and then see the output of each cell, which is kind of fun. And it's what all the cool kids use in machine learning because you can also display images and do training and stuff like that. You can do a lot of stuff, and it's just fairly intuitive. Okay, when you're done using the environment, you want to deactivate conda so you don't accidentally use it on your next project. And that's done by running conda deactivate, which is easy. in that previous example, when you're in your CoreML, when you deactivate it, you'll see it go back to base. If you run conda deactivate on base, it still stays in base because there's nothing to deactivate. Other handy conda commands, we're just going to sort of go through this fairly quickly, but conda list will list all the packages in your currently active conda environment. Conda update package will update a particular package. Remove package will remove any packages that you list there. Conda environment list will list all your conda environments. And in the list, it'll also put an asterisk next to the one that's currently active. Conda environment remove name will remove the environment and any packages that were installed to that environment. And luckily, there's a conda cheat sheet, so you don't have to remember any of this stuff. This link is a big link to copy down, but it'll be available in the slides when I post them online later. It says it's for conda 4.6.0, and currently conda is on 4.11, I believe, but it seems to be fairly standard, so everything works there, as far as I can tell. And I use it constantly. All right. It's also going to be important that you check your Python path and version, because I have seen situations where it did not install completely properly. But what you're going to do is you're going to type at your bash shell or your CS shell, which Python, and you're going to want to see a homebrew path if you installed it via homebrew, like we showed here. And you'll also see the CoreML, the environment name in that path too. So you want to make sure that Python belongs to the path that you're expecting. You can then run Python version to find out which version you're running. In this case, 3.9.7. If you see 2.7, you're probably running on the system Python that came with your Mac, which is bad. You don't want to use it. It won't be able to run most of the scripts or even Coreml Tools, I don't think. You can also check your library versions that you have installed via the Python interpreter. So the interactive interpreter, when you type in Python by itself with no parameters, you'll enter the Python interactive interpreter, and you always notice these 3 arrows as a prompt for that. And for that, for instance, you can import Torch, and then you can run Torch version to get the version back for that. And then you get a string back with 1.10.0. And you can do the same thing for Coreml Tools. We can import it and then see what the version is to make sure that we have at least something greater than 5.0. Yes, anything older will not work probably. I think older than 5.0 won't work for what we want to do today. And Torch version older than 1.10 probably won't work either. All right, let's take a look at the conversion script that we'll be writing together. If you want to follow along, I have a GitHub repo that has the conversion script already done in it. We're going to be going over a couple of steps at a time just to see the whole thought process and what happens when you only do a partial conversion and stuff like that. But if you want to follow along, there's the GitHub link. It'll be available also later at the end of the presentation. Okay, so the first thing that we want to do in our script is we're going to import Torch and import Coreml Tools. And this time what we do is we import it as CT, just because as a software developer, I'm lazy and I don't want to have to type in Coreml Tools every single time I want to use it. So I import it as CT, so I can just type CT dot whatever. But before we continue, one more thing I need to mention. So the Python script that we're going to be writing, you could run in the interactive interpreter line by line and it'll work. But when you import Torch, it'll be fine. But when you import Coreml Tools, you might see a warning. And in the case, it's saying that the Torch version 1.10 that we have installed has not been tested with Coreml Tools, and we may run into problems. So they've only tested on Torch 1.9.1 because Coreml Tools lags behind. They can't test immediately after a new Torch version has been released. So anytime you're using a newer version that they have tested on, they'll show this warning. Most of the time, it's not a problem. And in fact, this time, if you tried to use Torch 1.9.1, the conversion process would crash. I actually updated to 1.10 in order to get around a crash with the conversion process. So that's kind of ironic. All right, back to our script. We've imported Torch and Coreml Tools. We're going to import sys. Sys is just a very generic system package that comes built in with Python. We're going to be using it for command line arguments and to early exit the script. Speaking of command line arguments and early exiting, we check to make sure that we have at least two items in our argv list. And that's because the first item is going to be the name of the script, and then the second item is going to be the parameter that we want, which is going to be the image size. So in this case, what this script is going to do, we're going to make it so it's a little bit user-friendly. And that when you run the conversion script, you can pass an image size and create a model for that image size. So let's say you want to use images of 512 by 512. You would pass in 512 for the image size, and it would create a model, a CoreML model that will take in images of 512 by 512 and output model images of 512 by 512. You can do larger images to, like, say, 1024. However, those will also run more slowly because there'll be more pixels to process. So, but this allows you the option to create whichever models you want and test them out. We're going to store the size that the person passed in by converting the system argument, the first argument, to an integer and store that into size. Size is all caps just because I wanted to differentiate that it's not a variable, it's a constant that was passed in as a command line. We're then going to load our PyTorch model. And this is the one-liner that I was talking about. And in this case, we're going to tap into the loading function from Torch Hub. And the way this works, when you if a GitHub repo has that hubconf.py, you can pass in the GitHub repo and the branch, as you see here. So the GitHub repo is Brian D. Lee /animegan2-pytorch. The branch is main. Generator is the name of the function that Torch Hub load should call that's in that hubconf.py file. So inside Brian's hubconf.py file, he has a function called generator, which creates the model and returns it. So this is the function that is used to create the model. And pre-trained is an argument that his generator function takes. And pre-trained, we're going to set it to facepaint 512 version 2. That's the one that we saw generate all of those awesome images. The pre-trained means those are the parameters for the model that have already been trained to create pretty pictures. And it's the weights and the biases. If we were to not set up, if we were to just get random weights and stuff like that, the image that would output would probably just be garbage, random noise, or nothing. So, and luckily he provided this pre-trained model for us. Okay, we then set the model to evaluation mode, eval. And the reason for this is we're not going to be training the model, we're just going to be evaluating it. And when we put the model in eval mode, it can make some optimizations to the model that and throw away some layers and stuff that it doesn't need when it's not training. So that'll help make things more optimized for inference, which is just running inputs into the model and getting the outputs. So it should hopefully be a little bit faster. We then are going to create a dummy input for the model. And for doing this, what we're doing is we're using a function called rand on the Torch module. Rand just basically creates an input of a specific size that you specify, and with random values between 0 and 1, I believe. And the size that we pass in is 1, 3, and then size. Size is the variable that stores the command line argument that was passed into the script. The reason we want 3, so 3 is the channel, so RGB. Size is the width and the height. But what is 1? This is a batch size. And because models generally they run on GPUs and stuff like that, you can run batches of input at once because GPUs are highly parallelized or parallelizable. In this case, we only care about one at a time because we're only going to be feeding it one image at a time. This dummy input we're going to use to trace the Torch model. And the reason is to convert a PyTorch model into CoreML, you have to get you have to have what's called a Torch script. A Torch script is this PyTorch model that we have up there. It contains the parameters and it's loaded in the structure. But the file itself, if we were to save that model immediately at the very top, we would just have a file with all the parameters in there, but not the actual structure of the model. The structure of the model comes through the code. This torch trace function traces out the structure of the model and adds that to the model information. So this trace model that we have coming out of this function is going to have the model's parameters and the structure. And what we're doing with the trace is we're basically sending that dummy input into the model and watching how it behaves in the model and capturing that information. This takes a little bit of time to run, but it's once it's done, we want to save this to a PT model. Sorry, a PT file. You can call it whatever you want. Like PT or PTH are the standard extensions for PyTorch. And this is specifically a torch script type of model, which I said. Okay. We're then going to create an input using we're going to create a Coreml input. So bear with me. This is a lot of work initially, but it'll be worth it in just a minute. So we're going to create this tensor type input from Coreml Tools, and the name we're going to call it input, and the shape we're going to take that same dummy input that we use to trace the PyTorch model, and we're going to take the shape from that to tell Coreml Tools what shape the input should be. We then can convert the model, the torch script model, by passing in that file that we saved and passing in the inputs that we have. And this single line is going to convert that PyTorch model into the Coreml model. So we can then save the model. And what we're doing here is we're saving the name of the model and we're putting the size parameter into the name of the model so that we can differentiate it in case we create multiple sizes. Okay, let's take a look at something. All right. All right, so this is the model that we just created from our script. This is opened in Xcode now. And if you look, you can see a couple of random things. So metadata is fairly blank, except it tells you like the Coreml tools, the torch version that you use to generate it, and the Coreml tools that you use to generate it. You can see that it computes using float 16 bits, but it stores them as float 32. And you can see a list of the most common layer types and their counts. If we go over to the predictions tab, you'll see our input is named input. It's a multi-dimensional array of float 32s, and the size is 1 by 3 by 512 by 512, which is exactly that dummy input size that we set up earlier, where we said 3 channels RGB and width and height of 512, 512, and 1 is the batch size. And the output is called var_440, and it's also multi-array. Okay, this is a good start. We could theoretically use this model in our app, but we can do better. So let's see what else we can do. Oh, before we do that though, if you were now to open up, so there's an open source tool called Netron, or a free tool or open source, one of those two. It's still free. You can view the structure of machine learning models, and it handles Coreml, handles PyTorch. I think it handles TensorFlow too. But on the left-hand side, you'll see the original PyTorch model. And on the right-hand side, you'll see the converted Coreml model. And you'll see some similarities and some differences. So we start off with this input. On the Coreml model, we have the scalar, because we're going to take care of scaling our inputs in the appropriate range right away, or it automatically adds that anyway. So right now, I think it's just a 1. We have this padding, and this padding layer is the same. This convolutional layer and this convolutional layer is the same. This group norm is nowhere to be found here. And that's because that's that newish layer I told you about earlier. And what Coreml did was it took this group norm layer and converted it into this entire block here. And this is all the operations it took to create that group norm. It seems like this could be optimized further, but I think that's going to be an exercise for another day. I tried going down this rabbit hole for a while, and I got somewhere, but not far enough, and I had to backtrack eventually. But I might continue seeing where I could potentially optimize this a little bit more later. And then this leaky ReLU is a type of activation. This is the activation thing, padding. So it starts to see start to see the structure is matching. So it's roughly what we expect. It's a good way to debug the structure of a model visually if you want to see if anything is completely off or not. I want to go back also to trace. So we talked about tracing the model, and we can do that in this model. So I said that tracing uses the sample input and it traces the operations as they're performed on the data, so that it knows what the structure of the model is. This works if you have a simple model that does not have any control or conditional operations, because in that case, you're giving it a constant input. And so all the operations through are going to have deterministic results. So if there's any kind of conditional in your model, it's going to pick path A or path B potentially. So if our model had any of these conditionals, we would not be able to use trace in order to create the model. We'd have to use script, which is essentially, earlier we had torch.jit.trace. We'd have to do torch.jit.script. JIT stands for just in time. Not sure why that's relevant, but Apple's recommendation is to trace as much of the model as you can and script only the parts that you have to. So you can kind of combine the two too if you really need to. And the reason is because trace is going to create a much simpler, more efficient model overall than script will. Script might be a little bit more convoluted and add extra layers where they may not be necessary. All right, and because this is the actual structure of Anime-GAN version 2, you can see there's no conditional. It's just a straight line from the input on the left-hand side through all these convolutional layer norm ReLU layers all the way back. And then it starts to, basically what it does is it kind of converts the model down into a longer and longer, but smaller and smaller matrix, and then builds it back up to an image. So this is called, like, in the middle you have your bottleneck, and then it's going to blow it back up into your anime style at the very end. But because this is very linear, there's no control whatsoever, we can run that trace. All right, that's kind of an aside. All right, let's fix the input type, because that input type was a multi-array, which, while you can deal with it inside an iOS app, it's kind of annoying, and it's can be a little bit inefficient if you do it yourself. If you can fix the input type, you can have iOS and the APIs deal with the conversion for you, which is much nicer since, again, software developers were lazy, right? Okay, so if we go back to our script where we had these 3 lines, we had the input type from Coreml, not the dummy input type, but the Coreml input type, or the Coreml input variable. We had the convert call, and then we had the save, right? What we can do here is we can change the input type to be from tensor type to image type. And while we're there, we're going to add a couple of other parameters to it so that we can make our job even easier later. So we're going to add a scale of 1 over 127.5, and we're going to add a bias of -1 on all 3 channels. And what this is going to do, the combination of the scale and the bias, is it's going to take our 0 to 255 value pixels and convert it to -1 to 1, because this model actually requires that the values be between -1 and 1. So we're just normalizing them. The color layout we're going to say is RGB, not BGR, because some people train their models on BGR instead of RGB, which is not fun if you don't know. By not fun, I mean it's not fun when you don't expect it to be BGR and you run RGB through it, then your colors look all weird coming out. And this channel's first is setting to true. We're setting it to true. It's actually defaults to true, but that's because we, as you remember in the dummy input, we had the size was batch, channel, height, width, and the channel came before the height and the width. If the channel comes after it, then you have to set this to false. But PyTorch was channels first too. So TensorFlow, I think, does channels last. All right, then we convert the image again, and we save it, and let's take a look at what this looks like. Oops. Okay, so the next model looks like this. So everything looks kind of the same here, but when you go to predictions, you'll notice it now says the input type is image, color 512 by 512. Okay, this is great because now that we've changed the input type to image and we had it scale automatically within the model, we can actually just send, when we use this in our iOS app, we can just send it a CI image, a CG image, or a pixel buffer without any problems. And iOS will convert it to the values it needs to run through the model. So that makes things a little bit nicer there, but we still have some other problems that we can work on. For instance, this output is still a multi-array. And again, those are not fun to deal with. So let's see if we can change that. All right, so can we do better? I kind of hinted at that already. Yes, we can. We're going to edit the model now. And that's because changing the model input was easy. We can just change the input that we pass into the convert script, but changing the output, sadly, is not as simple as setting a parameter on the convert script. We have to get into the nitty-gritty of the model. So let's change the output type to be an image type instead of a tensor type again. All right, so everything in our script right now is fine, but we need to import a couple more things. This is a bunch of gobbledygook on the top there. This Coreml Tools.proto.featuretypes PB2. It's because, yeah, naming things in software is hard. What's important to know is that our feature types for setting our output and inputs are stored in this module submodule structure. And then we're also going to import Coreml Tools utils. And I'll show you why. Okay. The first thing that we want to do is we want to get the model Protobuf specification. That's an interesting combination of things. This is what's going to allow us to change and edit the output layer type. You could also change and edit the input layer type this way too, but we were able to take care of all that automatically. It's important to note that this function gives you a deep copy of the specification. So that means anytime we change spec now, it's not going to automatically change our ML model. So that's important to keep in mind. The first thing that we do is we want to make the output an image type. So we take the spec.description.output. We only have one output in this model, which is our output image. Hopefully it will be an output image soon. So we can just take 0 and hard code that in there. And this output now contains the description for our output. We want to change the type. So because it's a protobuf, you can just type and then type image type, and that will suddenly change the type of the output to be an image type. So by just typing in this line right now, it's going to change it to an image type, and simultaneously we're going to set the color space to RGB. So we've taken that feature types PB2 that we've imported as FT because it's much shorter. We can set it to image feature type and set it for type RGB for the color space. We're going to change the image type's width to size because otherwise it doesn't know. We change the image type's height to size because otherwise it doesn't know. And then we use this utils module that we imported to save the Protobuf specification as a new ML model. And this is different from how we saved the ML model before. The ML model before, we saved by doing mlmodel.save and giving it a name. This time, we actually have to save the specification, which will give us the entire model. But because we did a deep copy on the specification, those changes are not in the ML model. They're in the spec now. Okay, so let's see how this looks. And this is interesting because now we have a new tab. If we go to predictions, you'll notice that we have input image, color 512 by 512, output image, color 512 by 512. We have this new preview tab, which is cool. Because this model takes an input image, it takes images in and output images, Xcode automatically infers that it's some sort of style transfer or stylizing model. So it gives us this preview layer and lets us just drag in test images and see what they look like on the output. So let's just go ahead and take this here, let it process and see what our output looks like. Crap, black. Okay, original is right, stylized is black, which is not good. The reason for that is you remember that on the input, we normalized our inputs from 0 to 255 to -1 to 1.0. On the outputs, however, we're still getting -1 to 1.0, which interpreted as pixels from 0 to 255 is just going to be black. So we need to somehow get our values in the proper format or in the proper scale. And again, you could go back in iOS and do this, but that would be slow and painful. But we can also do this by modifying the model a little bit more. So let's do that. Okay, so we're going to scale the output. Starting from where we were at the bottom of our script again, we're going to get the neural network specification from the specification. So the specification contains a description of the entire neural network. And under the neural network object here, there's a thing called layers. And if we get the last layer, which is in Python, to get the last element of a list, you can just do -1. If you want to get the second to last, you do -2, the third to last, -3. So you can attack a list from front or back fairly easily. To get the current output layer, which is an unscaled output layer, we just do -1. We add a new layer to this neural network layers structure. And at the same time, we assign it to this variable scale layer. This is going to be the new layer that's going to scale that unscaled output layers. We're going to change the scale layer's name just so it's easy to deal with. And then we're going to we're going to change the scale layer's types. Scale layer is, again, this Protobuf specification type of object. So by adding a dot activation, by accessing this dot activation dot linear, we automatically change the scale layer type to be a linear activation type of layer. And the linear activation layer, we have two parameters, an alpha and a beta. And as you can see in the comments there right above, I have the function for this activation, this linear activation, is just y equals alpha times x plus beta. So x is your input, y is your output, alpha, x, beta. So we know that x is going to be between -1 and 1. So if we set alpha to be 127.5 and we set beta to be 127.5, that's going to make y's range be between 0 and 255. We append the output, the previous outputs layer output. So the layer has an input and output. Previous outputs layer's output, we append that to our scaled layer's output, which sounds a little bit redundant, but right now the scale layer is just a function essentially, right? And we have to tell it where the output should go. And so we're basically hooking it up to the previous output layer's output. We then need to connect the previous layer's output to this new scale layer's input. So we change the name of the previous layer's output by setting it to scale layer input. It could be anything you want, it's just a string. And then we append that to the scale layer's input. And now we use, again, the utilities.save spec function to save our specification into a new model. So let's take a look at this one now. Okay, so again, we have predictions, same as before. We have preview. Let's see if our preview now properly converts my face into anime. Success. So now we know we have a model that will take an input image in CI image, CG image, or pixel buffer, CV pixel buffer format, and it will output an image for us to use. It'll output this as a pixel buffer. Great. So we're done, right? Oh, there's a little bit more that we can do. So what is the problem? What is the problem that's still here? Part of the problem is this output's name is var 440. That's kind of ugly. Let's see if we can change that. Because I'm very picky with my details. So let's rename the output. Okay, starting back again where we were. the output was from the previous part of the script. The output was the output of the spec. So there's the spec.description.output. So we're going to set the name, or the first output. So we're going to set the name to be output to make it something reasonable. Right now, before this step, it was var underscore 440. We grab the very last layer from the neural network using the -1 trick, the one we essentially just created. We set the name of that output, that layer's output, to be the same name that we just created. And we save it. That's it. So now, when we take a look at our model, we have a very nice output name for our model's output. This is, for here, it's a little bit more cosmetic, but if you have a model with multiple outputs, it's actually kind of important to know which output refers to which part of the model that you want. So if you had var 440 and var 489, then it'd be kind of annoying to figure out which one is which or to remember which is which. This makes it just a little bit clearer. There's still something that we can do to improve this a little bit better. So you'll see that this model is 8.6 megabytes. And you'll see that, as I mentioned before, it computes in float 16s, but it stores all its values as float 32 bits. I think we can probably save some space this way by changing the storage to be float 16. So let's do that by quantizing the parameters. Quantizing the parameters just means to convert the parameters from one format to another. And usually it means to compress them into fewer numbers of bits. So for this, we need to import a new function, which obviously I knew off the top of my head, didn't have to look up at all whatsoever. Yeah, so we can import that at the very top of the at the file. There's some code in between there. After we've converted our PyTorch model to an ML model, which happens now. This is already there. This is not new code. This was already in the script. We can then run the quantization utils, quantize weights function. And we pass it the ML model and the number of bits that we want to quantize the weights to. And this can be 16 or 8 or 4, or I don't know if we can do less than 4. I'm not sure that would be very useful anyway. But the less bits that you use for your weights, the less precision you have in your weights. So it may affect your output, it may not. It depends on your model. So this is on a case-by-case basis. But since we want this to run on the neural engine and on the GPU, we need them to be 16 bits anyway. And because it's already computing in float 16, it doesn't hurt to store them in float 16 either. So all this is doing is actually saving us a little bit of space on the model, and it also allows for a faster model load time since it has less bytes to read off disk. Okay, so if we open up the final model here, we'll see that at the bottom here, the precision is now float 16 and the storage is float 16. So our model, and it didn't change the effect at all. We can still drag an image here and watch it process. And it looks pretty cool on the output. We can drag another one if we want. I don't know what, I have lots of images of myself. This was me in the water. So that's kind of cool. Everyone likes this. I had an interesting idea to try taking a cartoon image of Miles Morales and then running him through this, and it's simplified it. But if you also notice, it made his eyes bigger again. Anyway, enough of that. Okay, so let's compare the outputs, because we've had a model in PyTorch, we have a model in Coreml. Just because we have these two models and we've converted from one to the other doesn't mean that they have the same outputs. It could be that there was an error in the conversion process. It could be that the precision used on one versus another is not the same. It might be that there's slight differences, and we have to see if we can live with those differences. So here are two original images. And first I converted them to PyTorch using just Python. You can just run these images through Python, and then through Coreml, and they look pretty good to me. I wrote a script also to compare these outputs and save them like this, but also to compare them numerically. And what I did was I thought, if I can flatten each of these images into a single 1D vector, I could then run cosine similarity between two vectors to find the angle between them, and then figure out how close they are to one another. And the top one, there is a 91.04% similarity, and the bottom one there's a 80.48% similarity. But that might not be very useful to see, because if I just look at those numbers, I'd be a little bit worried. But when I look at the output, it looks fine. So it depends on what your project is or what your goals are for your model, which similarity comparison you want to do. Okay, let's look at iOS integration. This is probably what you've all been waiting for. We're going to use Vision, so I'm going to quickly go over the Vision pipeline in case you're not familiar with it. But in running an API through the Vision pipeline, you start by creating a request. You pass it to a handler, and the handler passes the result or returns the result back as a property on the original request object. These requests can be anything from detect human hand pose, face rectangles requests. The one we're going to be using is the one at the bottom, the Coreml request. The handlers, there are two different types of handlers. There's an image request handler, and there's a sequence request handler. The image request handler works on a single image at a time, and the sequence request handler also works on a single image at a time, but it's meant for running on frame after frame after frame of a video where a previous frame might help it to do better detection on the next frame. So if you're doing like object tracking or something like that. The results are named analogously to the requests. So you have human hand pose request, you have human hand pose observation. Your Coreml request, the observation is going to depend on what kind of model you have. So we're not going to have a classification observation. We're going to have a, I believe it's a VN pixel buffer observation, because we're creating an image from an image. Okay, with this in mind, let's go over how to do this in code. So we're going to set up the request for our Coreml model, and we're just going to generically call it a VN request. We're going to create an ML model configuration. This configuration, we're going to set a couple of properties on it. We're going to set compute units to .all. This is actually the default, but I wanted to show you that there are options here. So it can be .all, it can be .cpu and GPU, which means it'll try to run it on the CPU or GPU, but not on the neural engine. .all will run on, it'll try to run on the neural engine first, or the GPU then, or then the CPU. Or you can say .cpu only, which would then force it to run on the CPU, which I don't know why you would want to do that, but in this case, it's a terrible idea because it'd be very slow. The next configuration parameter is allow low precision accumulation on GPU, and I've set that to true. We're running in floating point 16-bit mode. This documentation was not entirely clear as to whether the calculations, though, are done as float 32 when it accumulates the values. And if that's the case, that would take a little bit more time because you have to convert from float 16 to float 32 and back and forth. I've set this to true because through testing, it seemed like it didn't affect the output that much. And I think it's also a little bit faster, but this is just something that you can test. We then need to create our model. So you'll notice that this is called Anime-GAN v2_512. That's because when we imported our ML model file into our Xcode project, it'll automatically create a class by the same name as the file name, which is Anime-GAN v2_512. So we can create an instance of this model by passing in our configuration and then accessing the .model property. I've done a shortcut by just doing a force unwrap on the try because, you know, YOLO. I mean, if this model doesn't work, the whole point of the app is pointless anyway. So might as well crash. We then create our Coreml request from this model. We have to first convert it from the Anime-GAN v2_512 to a VN Coreml model. Actually, I think the model type that we had up there is actually called an ML model. But so we have to convert it to our Vision Coreml model for our request. For our request, I'm going to set the image crop and scale option to center crop. That just basically means it's going to crop the center part of your image as much as it can, but it's going to keep it as a square because our input to our model is a square. And so we don't want to feed the whole thing in there. This helps it This helps it run a little bit faster too, because I think cropping is faster than scaling. And then we're going to return our request. So this is just our private request variable in some sort of class, potentially. How do we use this request? Well, in some function later on in this class, we can create our VN image request handler with our frame from our camera, which is a CV pixel buffer. It could be a CI image. It could also be a CG image. You just have to update the call for here. Lost my train of thought there for a second. Yeah, the reason it's an image request handler is because knowing the previous frame does not help us to generate anime for the next frame. So there's no point in using the sequence request handler. We're going to perform our request that we just created up there. So the image goes into the request handler. The handler then performs a request, which contains our model information. And we're going to get back our anime request. And on the anime request, we have results in the form of VN pixel buffer observations, an array of them. We only care about the first one because there's only ever going to be one output from this model. So we also make sure that we grab the first one into result. And then we can create a CI image from the CV pixel buffer that is the pixel buffer property on the result. Okay, so I'm going to try something a little bit stupid and crazy. I'm going to try some live coding in the hopes that we can do some cool stuff. Or how are we doing on time? Are we doing okay on time?
And we're 80 minutes in.
Oh, wow.
So
okay.
I think we're okay. A few people have dropped, but
oh no. Okay, I broke them. Okay, because I could also just skip to the final product, but let's go for it. Okay, so here is our camera application that's going to Anime-ify yourself. I'm going to run it on the Mac so you can see what it does. Okay, there I am again. So right now, all it does is it shows the video of me. So it's capturing from the camera on my Mac, and it's displaying it in our app. Okay, so when we go to, I have created already this, we have this AnimeGAN 512. I have an AnimeGAN 1024 too, but it's a little bit too slow. So we're going to stick with the 512. This has the same preview thing that we could do, just like I said. And here's, if you wanted to see that model class that it generates automatically for you, you can click there and see the automatically generated code. Okay, I've created a class called a vision processor, which does a perform a request. It's a protocol that does a perform a request. I've done an extension, protocol extension on it that generates that image request handler on the image, which is passed in, which is a pixel buffer, and performs the request and returns the request. This is just so anything that conforms to vision request, the vision processor automatically has this functionality in it and simplifies it. So we have this class anime generator, which conforms to vision request, vision processor. So the first thing I'm going to do is I'm going to create that request, private property that we had there. Let's see if I can copy and paste some stuff. Oh, that did not work. Okay, so yeah, well, we can do the let configuration config equals ml model configuration. Config dot set this to true, set the allow local position, and then compute units to dot all. Okay, and then we're going to have our model. We're going to pass in that model there, and we're going to create our request type. For our model. And then we set the image scale option to center crop and return the request. Okay, so now we have our request here. This is great. It's unable to infer closure. Oh yeah, but we also have to do that. Okay. Then here's our processing function in our anime generator, where we pass a pixel buffer. I check to make sure that it's not a, so we have an optional for simplicity. I make sure it's not nil. I check a processing variable here, because if we're in the middle of processing an image, we don't want to start another processing session, because that will just really slow it down. So then we set processing to true if we're not processing, and we defer processing equals false. And then all we have to do is we get our let anime request equal to perform request on image. So we're performing, oh, sorry, it's not, this just takes a single request. So we take the single request and we perform the image on it. So this is our request that we generated up here. And then we want to check our results. We want to make sure that they're vision pixel buffer observations. And we want to make sure we have a single result. Otherwise, we return no. And then we return our result here. No, sorry. We can't return the pixel buffer. We need to return a CI image from the contents of a pixel buffer. And that was from our result. Dot pixel buffer. Okay. So now we have our processing, our anime generator processing. If we were to go into our main view model here, and in here we're adding a frame. If we were to add a new published, so the frame is what we're currently getting from the camera. If we're going to add another published variable called anime frame, and also a CG image, then we can, in our, we have a setup subscriptions function right here. We're using combine because I hear that's what all the cool kids do. No one uses that async await stuff. We can do our current frame from our frame manager. We can, let's see, what do we want to do here? We want to sample every fifth frame. So this is in my extensions, my publisher extension, I have a function that samples every X frame and default starting at 0. So this just will throw out the frames in between if you don't want to run as fast as, say, full frame. And because this model is not fast enough to run at full at your full frames per second, your full 30 frames per second, I just take every fifth one. Then we can compact map that because we want to convert that into a CG image by running. We want to first generate our anime image from our thing. So we're going to do let's CI image equal to anime generator dot process. Nope, shared because it's a singleton because I'm awesome with singletons, and we pass in the buffer. Otherwise, we return nil. Okay, now we have a CI image, but we need a CG image from that. Luckily, we have a CI context here that we can just tap into and return self.context.create CG image from CI image from CI image extent. So now we're converting our CV pixel buffer from our frame, passing it through our anime model, getting a CI image back, and then converting that to a CG image, which can then be displayed. So we can sync that. into self.animeframe. And then we want to store that in our subscriptions. Okay, so if we go to our call come through, right? Yolo. I guess we can, since we are a guard already, might as well be a little bit safer. So now in our main view, where we're looking at our model frame, we can change this frame to be anime frame. And if we run this, we now see me in anime mode, which is pretty cool. We can do one thing, I want to tweak one little thing more on this, and that's to show you side-by-side videos. So we can do that really quickly. I already have created a frame display mode, which has original, anime, or both. And there are some properties on there, computer properties that should show original, should show anime, based on which one of these it is. If we go into our main view here, we can just do an H stack. We can duplicate this, make this one the original frame. Oh, actually, yeah, I guess I don't need to go through all that. I can just show this and then, well, okay, come on. We're having fun, right? So if model.displayMode.should show original, then we show the original frame. If model.displayMode.should show anime, then we show the anime. And if it's set to both, then it'll show both of those. And we want to change that. We want to set the content shape of this to be a rectangle. And then on tap gesture. And the on tap gesture is going to call our model.next frame display mode. So now, if everything works properly, okay, so we start off with me in original mode. If I tap, I switch to anime mode. And if I tap or click again, then we get both of them side by side, and you can see a comparison of me and anime mode. So, yeah. Yay.
That's pretty cool, Yono.
Thank you. Do I have anything else? No. So yeah, GitHub repo has all of this on there. Thank you.